Hello, everyone. Welcome to the second webinar on this 8-part webinar series on anomaly detection using machine learning. So in the first webinar, the topic was doing data exploration to find out what is the appropriate anomaly detection algorithm. So we went through various cases and we talked about 4 different categories of data as far as anomaly detection goes. So I have listed those 4 here. It's either univariate independent or univariate sequential. By sequential, I mean autoregressive, like a time series. Multivariate independent or multivariate sequential. So the 4th one is the most complex one. The few points I missed last time, I want to quickly go over them before we jump into today's topic. One is when you detect anomaly, there are 2 kinds of anomaly detection output. Either it's a point outlier, that means a single point is detected as an anomaly, or it could be a subsequence outlier. That means a sequence of data is collectively is detected as anomaly. Example of that might be, for example, in medical device data, for example, ECG. There you might find that is sequence of, let's say, 3 or 4 data points are kind of anomalous. So the subsequence outlier only makes sense if your data is autoregressive. Now for independent data, just because, I mean, it may so happen that a bunch of points which are successive are detected to be anomalous, but that's not what I'm talking about when I say subsequence outlier. I mean, that's just pure accident. Subsequence outlier is something that's your goal. So you take a sequence length. Typically, in most of the algorithms, you take a subsequence length, which could be, 3, 4, 5, whatever, depending on your use case. And then using the algorithm, you find out whether that subsequence is anomalous or not. So it's kind of a part of the solution. So considering this, there are actually 6 different scenarios because for the sequential data, the output could be either a point outlier or a subsequence outlier. So taking everything into account, there are 6 different types of anomaly detection scenarios. Outliers can also depend upon the data context. It could be global or it could be local. When it's local, it only considers a small window which captures the the recent history of the data, and for global, it takes the complete data set into account. Anomalies also can be contextual. That means whether something is anomalous or not is very much dependent on the context. So for example, a retail company might be selling the same product in 2 different stores. So in this case, the store location is the context. So for example, what is normal sale in one store might be anomalous in another store. So you really have to take the context into account. So that's called contextual anomaly detection. Now, if your data has a seasonal cycle, for example, let's say your data is a weekly cycle. So that means, every day of the week, the data pattern is changing. So in that case also, it's a special case of contextual outlier because you can consider each day to be the context. So in this case, you might be building a separate model for each day, because what is normal in one day might be abnormal in another day of the week. So in that case, the day of the week becomes the context. So those are some of the points I wanted to make regarding the session 1. I also added this. I compiled all the resources that I referred to in this list here. So there's outlier detection survey paper, and then there's a more recent outlier detection survey paper, and then link to the Data Explorer Python class that we used last time, which is in my GitHub repo. And then the Python notebook that we used, it's also in my GitHub repo last time for experimenting with data and exploring data. So now off to today's topic. So today we are going to consider, out of those 4 cases, we are going to consider the first case, which is univariate anomaly detection. It's independent. That means it's not autoregressive. So that means the data is not a function of its, past data. So that's where, so it's not autoregressive. It's so I'm calling that independent. So what we're going to do today is do a review of some popular anomaly detection algorithm for independent univariate data. Details of running of one of the algorithms on Spark. Actually, I'll be covering 2 of them. Like I said, by independent, I mean the data is not autoregressive. The current value doesn't depend on the past values. But in reality, there is no crisp boundary between whether some data is independent or autoregressive. I mean, every data is autoregressive to some extent. I mean, the truly random data doesn't really exist in the real world. So it's not, the demarcation is not, very crisp. So all the algorithms that we'll be discussing today, they are based on the statistical model. So essentially, we train a statistical model, then we use that to detect anomaly. So the model could be either parametric. For example, for z-score, you have to build a Gaussian distribution model using maximum likelihood, or it could be non-parametric. It turns out that most of the algorithm that we'll be covering today, they use non-parametric distribution. So z-score is the most popular and most common one. So it assumes that the data has a Gaussian distribution, and whether something is anomalous or not depends on how many multiples of standard deviation the data point is away from the mean. So, and then you set a threshold, which might be 3. So for example, if you set it to 3, then if it's 3 multiples of the standard deviation away from the mean, it's labeled as outlier. Robust z-score is kind of an extension of z-score. Z-score is not, it's very sensitive to outliers. If you have outliers in the data, your Gaussian parameters like the mean and standard deviation will be seriously impacted. So robust z-score overcomes that. So instead of mean, it uses median. So what you do is you find the median in your data, and then what you do is you calculate something called median absolute deviation. So once you find the median, then you find the deviation of each data point from the median, and then you take the absolute value of that, and then you take the median of those values. So it's kind of comparable to standard deviation, intuitively. And then whether something is outlier or not will depend upon how far away the data point is with respect to the median. Again, as a multiple of the median, absolute median deviation. Empirical probability distribution, it's the concept is very simple. You just create a empirical distribution of your data, essentially a histogram, and then any data point that has very low probability is labeled as outlier. So in this case, the logic is that whether something is outlier or not, it depends on probability. So it disregards the magnitude of the data point. It disregards the value. I mean, the value will not necessarily be extreme values. So because your distribution can be anything, right? I mean, you may have a bimodal distribution, and then you may find a data point, in between the two modes with a very small magnitude, but with a very low probability. So that will be labeled as an outlier. So it depends on, like we discussed last time, it depends on what you define to be anomalous, whether should it be based on how extreme the values is or how rare the values is. So they're two different concepts. Now, as I said last time, if your distribution has a central mass, then your extreme values will also tend to be rare, but only if the distribution has a central mass. Interpercentile difference. So this is also another technique. So it depends, it's a function of the difference between the 75 and 25 percentiles, and also the difference between your data point and the 75 or 25 percentile values, depending upon where your data is, whether it's above your average or below the average. Accordingly, you choose the percentile. So it's a function of all that. Meta probability is something interesting. So what you do is you have a data point which has a probability value. Now you go through all the data points that have probability values less than that, then you add them all up. So that will correspond to your outlier score. Cumulative distribution is similar to the empirical distribution, except that it's cumulative. So do a cumulative distribution, and then you define some threshold. So for example, you might say that if it's above 95%, it's an outlier, or if it's below 5%, you set some critical values, and based on that you define what your outlier is. Extreme value statistics is what you do is you subsample your data. You essentially sample your data to find maximum values, and then using those maximum values and using a distribution called Gumbel distribution, which is for extreme values, you determine whether a data point is anomalous or not. So what we are going to do today is we are going to go through two use cases. So the first one will use robust z-score, and the second one will use z-score. So robust z-score is based on it's not even a distribution, you just calculate the median essentially. Z-score is obviously based on a parametric distribution, and it's assumed to be Gaussian. So the first use case is this. Consider a ticketing system, where people file issues. It could be a bug tracking system, or it could be some IT, ticketing service in some company. So what you do is, you file an issue, and then there is some. So to resolve the issue, it's going to take certain amount of time, right? So what we are going to do is we are going to analyze the time to see if there is anything anomalous, if there is any ticket that's taking unusual amount of time to process. So in this case, when I say unusual, it means it's taking far more than what it should be taking generally. So the service time is extremely high. So those are the so that's what we are going to detect using robust z-score. Now this data set has two more fields. One is the severity of the issue, and the other is the priority of the issue. Now the time it takes will also depend upon those two parameters. So strictly speaking, it's a case of multivariate anomaly detection, but today we are going to treat it like a univariate anomaly detection and ignore the other two parameters. So when we come to multivariate anomaly detection, we might use a multivariate anomaly detection with the same for the same problem. But for now, we are going to assume it's a univariate. The reason it's multivariate is because those two other variables, the severity and the priority, will also influence the time it takes to complete to resolve the issue. or the service time, right? The second one is for a server, it's the CPU utilization, CPU percentage. So here we assume that the data has Gaussian distribution, so we'll apply z-score based anomaly detection algorithm to find anomalous CPU usage. In this case, by anomalous, I mean something that's very high compared to what's considered to be normal usage percentages. When you have very high CPU, it might it could be for various reasons. It could be some unusual activity. It could even be some cyber attack or some runaway process running. There could be many reasons. So we're not going to look into the root cause or the reason behind it. All we want to do is simply detect any kind of anomalous CPU usage percentage. So that's all we are interested in. So, and here are the links for all the resources that's relevant for this session. So right now I'm going to jump to the Python notebook. By the way, all the implementations are on Spark Scala. So I'll be running them on my laptop with a Spark pseudo cluster with just one node. So ideally it should be running with multiple node cluster on the cloud, but just for the demo purpose, I'm going to run it on my laptop. So here is here's today's session. Okay, so this is the first use case. Again, we are going to find anomalies in service time for a ticketing system. So we'll review and explore the data set. All the data sets for all my use cases, they're all synthetically generated using Python scripts. We'll review robust z-score algorithm, which we already did. We'll also do a quick review of the Scala implementation of the Spark job. We'll review the configuration. All my implementations are heavily configuration driven. I use something called type-safe configuration, which is a JSON-like syntax. It's simpler than JSON. It's from a company called TypeSafe. It's an open source configuration management library. Then we'll actually run the Spark job. We'll then look at the output. So I'm going to go to a shell terminal. So I'll start Spark. And while Spark is starting, let's go through some relevant files for this use case. One is so all my Spark jobs, there is a shell script. So I run everything off this shell script. So the shell script will essentially run different Spark jobs. It has some other commands for various data operations, like copying or moving files. So everything is essentially in this shell script. There is also a tutorial document. Sorry, not this one. So which is also in GitHub. So it tells you, it gives you all the instructions on how to run this use case. So I'm just going to jump to this. I'm not going to go through this data generation steps and all that. So what happens with the data generation is that I generate some data, which is normal data. I use that to build the model. Then I generate another data set, which is the test data set. Then I artificially insert some outliers in that. So that's what I do. Now, it involves two Spark jobs. One is to calculate the median and the median absolute deviation. Now, this Spark job needs to be run twice, because when it runs for the first time, it calculates median. And second time when it runs, it needs the output from the first run, which is the median. It needs the median values to calculate the median absolute deviation. Now, my data has data for two different, let's call them service centers, okay? So there's a unique ID associated with each. So it builds two different models, one for each service centers. So the first field in the data set is actually the service center ID. So let me see. Yeah, I will take a look at the data later. So the first step is to run a Spark jobs to calculate median, and then to run it again to calculate median absolute deviation. Now, let me go through the configuration. So this is how the configuration looks for my Spark jobs. See this block here? So each block is for one specific Spark job. So a file may have multiple such blocks, one for each Spark job. Now, the one we are going to run right now is this one. Now, this string is same as the name of the Spark job. I can show you. So this is the actual Spark job implemented in Scala, which supports all those algorithms that we just talked about. See, this Spark job has this name, which matches with the name in the configuration file. So I have a Scala trait called job configuration, which does all the configuration management. So just given a configuration name and a file, it'll pull all the configuration data out. And you'll see in the beginning of the Spark job, it's all reading all kinds of configurations. Get config, for example, get mandatory string parameters. That means it's going to find a configuration parameter with this name, and it's mandatory. So that means if it's not found, it'll throw an exception. Anyway, let me go back to the. So here's the thing. So let me quickly go through this configuration. The first two are the delimiters for my input and output. Attribute ordinals, so which tells me which column has the data. So that means the service time. So I'm referring to all the columns by their index. So it happens to be the fifth column, which is, that's why I have a 4 here. I mean, I could have multiple data columns. So that's why it's an array. So if you had multiple data columns, then it will do the anomaly detection for each column. Seasonal analysis. So there is no seasonal cycle. So it's set to false. So the operation type, because this thing is run twice, once to get the median and the next time to get the median absolute deviation, you have to set the type here properly. When we get the median absolute deviation, it needs access to the median. So here is a file. So this file will have the median values for both the service centers. Remember, we had 2 service centers in the data. The seasonal stuff you can ignore. Time, which field is the time field? So it happens to be the second field in my data. So that's why it's 1. Output precision, you can ignore the rest. And then there is a parameter. There is a minimum sample count. So this job will require at least that many data points to run. If you don't have 100, then it'll just throw an exception and quit. So I'm going to run the Spark job now. So that's the script that we just looked at. And this is the command we are going to run. It calculates median. So it's starting the Spark job. So it calculates the median values. So we can take a quick look. Let me see. So we are running this output to get mstat. Say this is just the median value for one of the service centers. So, and the other one, the other file has the other one. So the first field is the service center ID, and then the 4 happens to be another, it has to do with, it has to do with the field, the column that we are using for our data, which is the 5th column. And the last one is the actual median value. So now what we are going to do is, we are going to run this into one file. So we'll run that. I'm sorry, I was disconnected for. Yeah, sorry. So I got all the output and put them into a file called med.txt. And now if you go back to the configuration, you'll find that, that file path is defined in this parameter. So it gets used next time the job is run. So we're going to run it again, except that change this to MAD, which is for median absolute deviation. So we are going to run the same job again. So again, we are going to consolidate the output into another file called mad.txt, which has the median absolute deviation values. Okay, so now, so essentially we have built our model. And the model is, in this case, very simple. It's just 2 numbers. the median and the median absolute deviation. So now we can do the prediction. For doing the prediction, we are going to run, this part job. Okay, and this service center ID, similarity, and then the score. No, I'm sorry. Yeah. Robust Z-score. Okay. Yeah. And this is the threshold 2.0. That means it's an outlier if the deviation of a data point from the median is equal to or more than twice of the average deviation that we found. So in that case, it's labeled as an outlier. I'll skip, yeah, let's see. See here, it's defining the two paths. So basically, this is the model for us. So the outlier predictor needs access to the model. So that's basically our model, these two small files. Seasonality, we don't have any seasonality, so those things are all set to false. Then there is a parameter called polarity. So the polarity has to do with what do you consider to be the outliers? Is it the extremely large values or extremely small values or both? So in this case, we set it to all. But in this case, you could set it to high also, because we are only interested in the high values as the outlier. We don't care about the low values. So we can go ahead and run the predictor job. So remember, for this one, we are using a different data set, which is a test data set. And we had some outliers inserted into the data set artificially. Okay, so it's run. So now let's go back to the notebook. So I've done a little bit of data exploration in the beginning. So for example, this is the data. This is the data set. The normal data without any outlier. This is the same data, just zoomed in just to see. So it's essentially random data. Doing a test for whether normalcy, whether the data is Gaussian. We know that it's not Gaussian, and and that's what it's finding. Here is the histogram, so obviously it's not Gaussian. It's some distribution, but nowhere close to Gaussian. Actually, the data set was generated using an empirical distribution by sampling a empirical distribution. So here, what I've done is I've taken that outlier output, and I'm actually showing the outlier for one particular service center, which has this ID. So I'm getting all the data values. So this thing is a Python generator that I have in. I have a file called util.py in the lib directory, and when you use that generator, and you can also provide a lambda function which acts as a row filter. So it's going to filter out only the where the first column is equal to this, which is one of the service centers. And I'm getting the X values the same way, extracting the first column. The data happens to be the fifth column, and the time happens to be the second column. And then what I'm doing is, if you look at the output, let me go back. So let's look at the typical output. See, what you will find is that two additional fields have been added to each row. So the input data was up to here. So for example, 23 means that was the CPU usage percentage. 0.045 is the outlier score. Okay. And we know that only when the score is above 2, it's supposed to be an outlier. See, here it's 2.227. So it's an outlier. And the last field is the label, N for normal and O for outliers. So what I'm doing here is I'm overlaying on the plot the points that are detected to be outlier by this red line. So that's the first use case. So the takeaway from this is that again, as I was saying, we are kind of cheating. This should have been treated as a multi-layer outlier detection, multivariate outlier detection problem. We haven't done that. So some of the takeaways from this is that I mean, our data has a timestamp, right? But that does not necessarily mean that it's a time series or it's autoregressive, okay? Because any particular value does not depend on its past value. So when you file a ticket, there is a timestamp, right? But the amount of time it takes for a given ticket has nothing to do with time it takes for the ticket that was filed earlier or or recently, right? So although there is a timestamp, but that doesn't mean it's autoregressive. It's not autoregressive because each data point is independent. So as we discussed last time, if your data set has multiple variables and you have a hunch that they might be correlated, then you need to do cross correlation analysis. And if there is significant cross correlation between the data points, I mean between the data columns, then you need to do multivariate anomaly detection. So univariate anomaly detection is not appropriate in that case. So that's the first use case. Now for the second one, again, let's take a quick look at the So the second one, for the z-score, we need the mean and standard deviation. So it uses a different Spark job. And this is the configuration for that, which calculates mean and standard deviation. So this data set has essentially data for 4 different servers. And also it has seasonal cycles. So for example, the usage has one pattern during the weekdays and another during the weekends. So the way the seasonality is dealt with, and by the way, this is not the only way, is that for each, so for the weekdays and for each server, for the weekdays and weekend, separate models are built. And then when you're trying to predict for a particular data point, depending upon the timestamp, you pick the right model and make prediction based on that. So since there are 4 servers, there are actually 8 different models that get built. So that's the configuration for that. And then this is the configuration for the actual predictor, which is similar to what we had for the last use case, except that we are using a different algorithm, Z-score, instead of robust Z-score. It does require a stats file, which is the output of this job, which has the mean and standard deviation for all those 8 models. 4 servers, and then 2 models for each server. One for weekdays and one for weekends. So we can take a look at this. You see there are 8 rows here. So the first one is the server ID, and then this one is, the second field is telling me what kind of seasonality it has. So this one happens to be weekday or weekend. Then the rest are all stats. It calculates all kinds of stats like mean and standard deviation, mean, max, and all that. So for example, I think this one is the standard deviation. Anyway, so there are 8 rows, and you'll find that, for example, this server ID, it's there twice in this. It's here again. So one is for weekdays and one is for weekends. So this gets used when we run the actual predictor Spark job, because we provide the path for this file with all the stats. So I'm not going to run the actual Spark job for this. I'll just show you the output. You run it exactly the same way. This also has a shell script here. So for example, you run this one for all the stats. Then you consolidate the stats file into all the stats, all the output from this into one file using this command. And then you run this one for doing the prediction. Again, the data is prepared the same way. We generate the test data, then we artificially insert some outliers, and then we run the predictor. So one thing here is that, let me quickly mention. So what happens for this particular use case is that sometimes it may so happen that the data set that you have for building the model, that data set itself has outliers. So that's going to have an impact on your model, right? So how do you deal with it? One is you can build a model using algorithms that are more robust for outliers, or you can run a 2-step process, and that's what I've done here. So what you do is you build a model first with the dirty data, with the outliers, then you make predictions, and then from the predictions, from the output, you remove all the records that have outliers. So that's your clean data. So that's why when you look at the configuration for this, you'll find that there are 2 parameters here. See, output outliers and then rem.outliers. So when I run it first time, I set these 2 to true. So what will happen is it will generate one file that will have only the outlier data, and another file that will have the clean data. That means that data set will not have any outliers. So then what we do is we take that clean data set, run this job again. So this time our data doesn't have any outliers. Rebuild the model, and then use that model to the prediction on the test data. So it's like a 2-step process that you have to go through. Because the first model you build has been negatively impacted with the outliers. So to kind of mitigate that problem, you use that model, detect outliers, remove those outliers from your data set, and use the clean data to rebuild the model, and then you use that model to do the prediction. So that's why this job has to be run twice in this case, and also this one also has to be done twice. And it's all clearly explained. There is also a tutorial document. All the steps are clearly explained there. Okay, let's jump back to the notebook for this use case. Okay, so what I've done here is that I've taken like one particular server, and then I've picked 2 days. So for example, this is the day of the week field. So 0 means it's a Monday. So 0 and 1, Monday, Tuesday, and 5 means it's a weekend, which is a Saturday. So I'm actually picking up data for different days because they have different distributions. And here are the distributions. So you see it has outliers because we have this secondary peak at the tail end of the distribution. So these are all outliers. So these are the 3 distributions for the 3 days that we picked for a given server. Okay, next what I have done is I have removed the outliers by running the predictor, rebuild the model. Then, so after you have removed the outliers, this is what the distribution looks like. So now that secondary peak is gone, so that means the outliers have been successfully removed. And once you have done that, then you can use this to rebuild the model and to do your actual prediction. Now, with this data, I was just curious, so I ran that normalcy test. So it's still, according to the test, it's still not Gaussian. Maybe because there's not enough sample, but I went ahead and ran z-score anyway. Maybe I shouldn't have. Maybe I should have used some other algorithm, but I used z-score anyway. I was hoping that maybe I should have removed more outliers or something, but the statistical test tells me that it's not happy. It tells me that it's still not Gaussian. I was expecting it to be Gaussian after removing the outliers. So here I'm showing the outlier again for the same server, for a given day. All the red lines are the outliers. You see the usage here. So this is the weekend data, so which is why the usage is at a much lower level compared to what we are seeing on the left side of the chart. And we need to build for each server 2 separate models. Now, if you had now if the usage pattern was changing on a daily basis, then in the worst case, you had to build 7 models for all 7 days of the week. But in this case, it just so happens that all the weekdays more or less have the same usage pattern, and the weekend has a distinctly different pattern. So that's why I built only 2 models. But it could be such that you had to build multiple models, one for each day of the week. So here is a case where your data is not very clean, it's dirty to start with. So you have to figure out a way to get around that. And that's what we did. We make 2 passes through the workflow to get around that problem. So in this case, this data is autoregressive. If you do autoregressive, actually, I did some autocorrelation. Let me see where they are. Oh, here. Huh. Interesting. I don't know what happened. Oh, see, I have some autocorrelation. So it's highly autoregressive, as you can tell from the autocorrelation. But just because it's autoregressive doesn't mean that you have to use some sequence-based algorithm. Okay, algorithm that predicts outliers, based on the most recent data. I mean, it really depends on your use case. Um, so just give me 1 second. 1 second. Sorry, I'm back. So what I was saying is that just because it's autoregressive doesn't mean that you'll use the sequence-based algorithm. It really depends on your use case. You really care whether a particular data point is anomalous with respect to what the past 3 or 4 data points are. Because in this use case, you're simply interested in the extreme values, unusual values. Whether it's unusual with respect to the most recent history is not something you're interested in. So you won't necessarily use sequence-based algorithm. It really depends on your the use case and your interest. So let's go back to the Google Docs. So here are all the references. The Spark Scala anomaly detection implementation, the tutorial, the shell script configuration. And then there's also a blog post that you might be interested in on that Spark job. So it provides, a lot of detail. Only documentation on that, Spark Scala implementation. So in this blog post, the use case is that CPU usage use case, which was the second use case for us. So I think that's about it, and that's where I'll wrap it up. And let's see. So are there any questions? I'm trying to open the chat box. So no, maybe Sharon?
Yes, Pranab, I'm just, yeah. If
yeah,
you have
so
any,
last time I saw something called Q&A. I don't see that.
Yes, yeah. Yes.
So,
you can leave your questions in the chat box or in the question and answer window.
I click on the chat box, nothing happens.
Okay. In case, I will notify you, Pranab. I'm just waiting for them to type their questions.
Oh, I see. Okay.
Hi all, if you have any questions, please make use of this time. You can leave your question in the chat box or in the question and answer window.
Okay, let's wait for maybe 5 minutes.
Yes, yeah.
See if there's
Sure.
any question.
Yeah. Yes, we will be sharing the link to the recording by tomorrow. Pranav, there's a question saying, is it possible to get some exercise for this session?
Exercise in the sense someone wants to try it out. Is that what
Yeah,
you mean?
I think so. That's a question. Yeah.
Yeah. So for that, I think the best thing to do is to go through the tutorial documents, and I provided the links in the Google Doc. So you can start from there.
Okay.
So both
And
use cases has tutorial documents in GitHub.
sorry. There's another question from Lata. It says like, how Outlier detection help in patient monitoring?
I'm sorry, can you repeat the question?
How does the Outlier detection help in patient monitoring?
Yeah, so I mean, it depends on your kind of data you have. So you have to go through this, you have to do some exploration before you can figure out what algorithm to use. So that was what we did in the first session. So depending on the outcome of your data exploration and analysis, you decide what the right algorithm is, and then you use that. For example, if it's something like ECG data, you'll probably do some sequence-based anomaly detection.
I hope it answers your question, Lata. If there are any more queries, please make use of this time. So we assume that there are no more any questions from your side. Pranab, I think it's good to call it off now, but we will be sharing
Okay.
the class recording very shortly, as well as we have shared a Google link here, which contains the class notes and other instructions for the class. And we will keep you updated about the next session. Thank you. Anything
Okay.
else, Pranab?
No, just thank you everyone for joining. Hope to see you again in
Yeah.
the next session.
Yeah. Thank you so much, Pranav, and thank you, everybody.
Sure.
Good day for you all. Thank you. Bye-bye.
Bye.